We're going to be looking at chemical equilibrium today, and we're going to do something crazy. We're going to disrupt it. We're going to stress it out. We're going to show you what Le Chateliers principle is all about. First of all, let's discuss again what is chemical equilibrium. Well, it's the whole idea you've got reactants, and these reactants are going to collide together. Remember, chemistry is all about collision. These chemicals then are going to produce products. Nothing new there. But it turns out that these products, as they begin to start building up, they begin to bang into one another, those valence electrons. And the next thing you know, the reverse reaction takes place. We start going the other way. Wait a second, I only thought it went one way. Not so. Chemical equilibrium is something that happens in chemistry with all these chemical reactions. All chemical reactions will reach some equilibrium. So what is that equilibrium? We have the reactants turn to products, the products go back to reactants, the reactants go to products. Well, we know that we've reached chemical equilibrium when the forward reaction rate is equal to the reverse reaction rate. And we can also look at the concentration of the reactants. They're not going to change. The concentration of the products, they're not going to change either. They're going to have a steady state. The chemical reaction that we're going to focus on today is going to be an acid-base reaction. It's going to be taking vinegar, which has acetic acid in it, and we're going to combine that with ammonia, acid-base. That will produce the product. So there's the chemical reaction. And once we put them together into the test tubes, voila, it's going to be going back and forth a little bit. But that's really not what the reaction's all about. This whole experiment is going to be looking at, let's disrupt it. Let's do something to it that's going to create now a new situation. That's Le Chateliers principle. There are three different factors that can disrupt a chemical reaction. We can change the concentration of the reactants either by reducing them or increasing them depending on what our situation is. We can also change the temperature. We can have a very hot temperature or a cold temperature. That's going to change this whole idea of going back and forth. Or we could have a change in pressure, which will apply to gases. In this situation, we're going to have an ice bath and boiling water. So it's going to be about temperature. What happens here? So by simply changing this one variable, now of a sudden we have to establish a second equilibrium. The first one was simply just mixing the chemicals together. The second one is what happens when we add or take away energy. Now keep in mind, in the midst of doing all this, we should be able to also predict whether or not this is an exothermic reaction or an endothermic. And you're going, oh no, not this stuff again. This is thermodynamics. Well, of course it is. Chemistry is trying to tie all the concepts together. Remember when we're looking at exothermic, it's the whole idea that a chemical reaction is going to have a negative delta H. Remember, that's the enthalpy. That's the amount of energy, the potential energy stored in the chemical bonds. And if we think about writing energy in that equation, it's going to be on the product side. In contrast to that, if we look at endothermic, that's where we have to add energy to the chemical reaction to get the thing going, so it's going to absorb energy. And that's going to be on the reactant side. So as we're looking at this chemical reaction, I want you to keep thinking to yourself, is it endothermic or is it exothermic? And I'll give you a little hint. If we're heavy on the reactant side, we're going to have a blue color to this little situation. See, I haven't mentioned one other thing. We're going to be using purple cabbage juice. That's our indicator. And that indicator is going to be changing colors based upon whether we're heavy on the reactant side. That's going to be a blue color, versus if we're heavy on the product side, that's going to be a green color. Write that down, really, really important. So with all that said, let's get started and we'll get a chance to see what chemical equilibrium is all about associated with Le Chateliers principle. It's time for some collisions. One of the things that's most important about doing this experiment is we want to keep the contents of each test tube identical. We've already put in 20 drops of purple cabbage juice into each one of those. And it kind of has a bluish look. You know, it's based on the tap water, what your color is going to start out with. That's your neutral pH, about a 7. Now what we're going to do into each one of these test tubes, we're going to add our very first reactant. And that's going to be our vinegar. Now the vinegar, as you know, has acetic acid in it. And what we want to do is put in exactly 15 drops. So let's go ahead and do it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And if you look at it, you'll see a very, very pretty shade of pink. Now that should not surprise you at all. Seeing that, that's an indicator that there's an acid in there. We're going to do the exact same thing to our second test tube. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right, we got it. So what we want to take a look at now is, are the shades of pink the same color? They should be. Everything is identical on both sides. Now, we haven't done anything as far as the chemical reaction yet, but keep in mind, the reason that we want these colors to be identical and the shades identical is because we're going to be looking at color to help us to determine whether or not this is an exothermic versus an endothermic reaction. So be precise. This is quantitative stuff now. All right, with that said, let's go ahead and start some collision. This one's going to be a little trickier because we really don't know how many drops is going to turn this thing into a shade of green. That's where we stop our chemical reaction. As soon as this turns any shade of green, we're done. Whatever number of drops we put in there for this number of ammonia, we do the same amount here for this test tube. So let's go ahead and see. We're going to do some counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to stop there for a second, and I'm going to stir it. And it's not a bad idea to do some stirring just to make sure everything is mixing the way it's supposed to. So there's my first set of 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's do a little stirring again. At this point, I'm not seeing much of a color change, but we know it will happen because, again, purple cabbage juice is pretty awesome stuff. Here we have the next set of 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, one thing that's kind of interesting is you'll see how many drops I use. You may find out you use a different number. It's all about your eyedropper. Different ones, there's a macro drip and there's a micro drip when it comes to eyedroppers. And in this case, we already got 30 drops. I've had some students where they do it, and after about 15 drops, it's a done deal. But we're not there yet, so we're at number 30. 31, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now I definitely can finally see some change. Notice it's now purplish kind of a color, bluish maybe, bluish purplish, but we're not there. I don't see any green at this point. So get our eyedropper back full so we don't run out of drops. We're up to 40. 1, 2, 3, 4, 5, 6, 7, 8. Definitely changing. There's 48. 49, 50, 51, 52, 53, 54, 55. Do a little bit of stirring again. I think we did it. 55. Notice it's important to stir. Initially it looked like, okay, 55 didn't do it, let's do another 5. And notice too, my increments get lower and lower because I know I'm getting closer and closer to that shade of green. So what we did here, 55 drops, let's do the exact same thing on this side. Fill up our eyedropper, and now it's time to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Give myself a break. You can see I know how to count. Isn't this great? 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55. I hope this works. Oh man, it's like magic. We have both of them with identical contents. Now, put your ear next to these test tubes. Guess what? Collisions are happening. We have the reactants colliding together. They're going to be producing the products. They collide together. The reverse reaction rate now goes back to the reactants. They collide together. The chemical reaction now is taking place, and now we need to give it just a few moments for it to reach equilibrium. All right, time to demonstrate Le Chatelier's principle. Both of our test tubes have a chemical reaction that have reached equilibrium. We took the ammonia, we took the acetic acid, and we produced the ammonium and the acetate. As I mentioned previously, the reactants, if it's heavy on that side, is going to have a blue color. If it's going to be heavy on the product side, it's going to have a green color. Now, the way that we're going to disturb the equilibrium is not by changing concentration, not by changing pressure. Remember, we're not dealing with gases here. Instead, we are going to just go ahead and change the temperature. And we've got really two different ways to do it. We have an ice water bath right here in this flask, and we have some very, very hot water in that flask. Pretty easy stuff. Since these have identical contents, I'm simply going to take each one and put them into a different temperature. Now, what in the world do you think is going to happen? Do you think they're both going to stay the same shade of color? Could they even change to a different color? Well, based on Le Chatelier's principle, think about exothermic versus endothermic as we consider temperature. If it's going to be exothermic, then we're talking about the energy is on the product side. If we increase energy, it's going to shift it in the other direction. On the other hand, with endothermic reaction, that's going to be on the reactant side. If all of a sudden we go ahead and we add energy, what's going to happen now? So if we think of exothermic, endothermic, it's going to be the same thing. Always the heavier side, wherever the energy is, shifts to the opposite direction. We're shifting the equilibrium. Now, we're not going to have to wait very long. We saw that both of them started off with the same shade of color. But when I go ahead and I pull them out, let's see what happens. When I take energy away, I'm going to get this color. When I add energy, I'm going to get this color. It appears to me that by taking energy away, I'm going to be forming a green color. And when I'm going to be adding energy, I'm going to get a blue color. So how does that work? Where is energy written? Is it on the reactant side? Is it on the product side? Well, the answer is, I'm going to let you figure it out. Okay, let's try this again and see whether or not we get the same response. So now I'm going to take this one, which is blue, put it into the cold water bath. And I'm going to take this one, which is green, and put it in the hot water bath. Remember, one of the things about science is it should be testable. It should be repeatable. So let's see what happens here. And this is one of those nice demonstrations. It doesn't take a lot of time to see some results, and it's wonderful when you have visuals. What do you think is going to happen here? We add energy, we go from a green color to a blue color. We'll pull it out. Looks pretty blue to me. Come over here, we take energy away, and we get a green color. I'm going to give you a few moments to think about it. We'll be back, and we'll give you the final answer. And the decision is, what do you think? Endothermic or exothermic? Well, again, let's take a look at what we got here. We put the test tube into the cold water. That's taking energy away. It's making it less. that side, whatever side the energy is. And notice it turns what color? Green. If on the other hand we add energy, makes that side heavier, it's now going to turn blue. Where is the energy written in this reaction? Well, let's take a look here. Once you see it, it's like, oh, this makes so much sense. Hard part sometimes is seeing it. If we think of it being exothermic, which just happens to be the correct answer, think of energy written right over here. What happens if we add energy? If I add energy, I put this thing into a beaker that's filled with hot water, it's going to shift the equilibrium to the left. It's going to increase the reverse reaction rate, and you're going to end up with blue inside of that test tube. We saw that. On the other hand, if we go ahead and we have still exothermic sitting over here, and we're going to go ahead and we put it in the cold water, well, now what's going to happen? It's going to make this side less because it's like taking part of the product away, and we're going to increase the forward reaction rate, which is going to give you a green color in the ice water bath. It's all about thinking about the teeter-totter, guys. Don't forget that illustration. Whatever side gets heavier, you always go the opposite direction. This is going to be true whether we're looking at a change of temperature, a change of pressure associated with gases, or a change in concentration. The heavier side is always going to have to relieve that extra amount by going the opposite direction. Hope you enjoyed what we saw here, a demonstration of not only a chemical reaction and some color change, but also Le Chatelier's principle. We'll see you again next time, and have yourself a great one.